Hello now. Today we'll be looking at assignment 10/11. And the reason I've labeled it like that is assignment 10 has no section to read, just a set of problems from sections 3.1 through 3.3. Assignment 11 gets into velocity. So basically that's what we'll be talking about, section 3.4. So let's do some recalling. Recall that f of a plus h minus f of a over h gives the slope of the secant line through the 2 points a comma f of a and a plus h f of a plus h. It is the average rate of change of f over the interval a to a plus h. Nothing new there. Recall further that the instantaneous rate of change of f at x equals a is the derivative of f at a, and it's given by the limit as h goes to 0 of f of a plus h minus f of a all over h, as long as the limit exists. So I thought I wasn't going to be writing that anymore, but I guess one more time just can't hurt. So let's consider straight line motion, which, as the title suggests, is motion that is either along the number line like that or along a vertical like that. And here's some information that we have. Let's let s of t be the position of the function at time t. So we have a couple of definitions to make. The displacement of the particle over the interval, let's go t to t plus delta t, just got it in, is given by the expression delta s, which is equal to s of t plus delta t minus s of t. Simply the difference between those two positions. The average velocity over the interval t to t plus delta t is equal to the displacement, which is a distance, divided by time. So that gives us expressions for displacement and average velocity. And similarly, what we have is the instantaneous velocity at t given by the velocity That's going to be the derivative of the position function, which is equal to the derivative expression. How many times have we seen this now? There we go. So average velocity over an interval is the slope of a secant line. Instantaneous velocity over an interval is the slope of the tangent line, which is what we call the derivative. And the speed of a particle is just the absolute value of the velocity. So I can also write it like this. You know, I think, that velocity is a vector. It has direction and magnitude, and so speed is simply the magnitude of the velocity vector. So let's consider a problem. A rocket is shot straight up with a launch velocity of 160 feet per second. So this is straight line motion. It's straight line motion in a vertical direction. And what we want to get are the different motion equations. So one of the things we know is that acceleration, which is the same as gravity, if we're in units of feet, is going to be minus 32 feet per second, which means every second the velocity is decreased by 32 feet per second. So what's the velocity? Well, we're working backwards here with derivatives. So really, since we know that acceleration is the derivative of velocity, what we ask ourselves is, what must the velocity be if the derivative is minus 32? Well, that suggests that the velocity is minus 32t. All right? But we know that there has to be a constant added, and that constant corresponds to what the velocity is when t is equal to 0, which we were told is 160. So there's our expression for velocity. We do the same thing for the position function. We ask, what do I take the derivative of to get the velocity? And you should see that that'll be minus 16t squared plus 160t plus whatever the initial position is. And I think in this case we're assuming that the initial position is at ground level, is 0. So once we have our motion equations for position, velocity, and acceleration, we can answer any question at all. So we'll do that now. So let's suppose the first question we want to ask is, what is the maximum height that the particle reaches? So what you should understand is that the rocket is going to get to its maximum height at the very top, and that's where the velocity changes from positive to negative. So at the maximum height, velocity has to be 0. Well, let's go back and take our velocity equation, which is minus 32t plus 160. And velocity will be 0 when t is equal to 5 seconds. So what's the highest that this goes? It'll be the position at 5 seconds. And if you do your computation on that, you should get 400 feet. Okay, let's consider one more question. When does it hit the ground? So if you think about that, it hits the ground when s is equal to 0, which means when minus 16t squared plus 160t is equal to 0, and that happens when t is 0 at the very beginning, or when t is 10. So we have 2 times when the particle is on the ground. at the very beginning and after 10 seconds when it hits the ground. So we've answered the question when it hits the ground. It hits the ground when t is equal to 10 seconds. So the follow-up question is, how fast is it going when it hits the ground? So really all we need to do then is to say, what is v of 10? And if we again do our calculations correctly there, v of 10 is minus 160 feet per second. In other words, the same magnitude that it was going when it was launched. So there's some interesting information about straight line motion, and we'll continue looking at questions like that throughout the course. What makes this question a little bit easier than some of the ones that are coming is that the acceleration is a constant. When we look at problems in which acceleration is not a constant, we'll have a little bit more fun. See you next time.